is the following statement going to be true, that the difference between the set A and A difference B is just going to equal to A intersect B? We have a kitty here meowing. Hi, what do you think? Well, what does it mean to take the difference of a difference? Well, let me show you how to think about it. You can sit down there. So the first case we should think of is probably the case where the two sets, A and B, share some things in common. So what does that mean? Well, so the first case we're going to consider is when our two sets, A and B, share something in common. So first, let's take the left-hand side and see what it means. So A minus B means you take A and you subtract all of B. So everything I'm shading, you don't want, which means what you're left with is just A with obviously everything here erased. So what you're going to be left with is the following. You erase everything I've shaded in, and you're going to be left with A having like this chunk out of it, right? So you'll be left with something that looks like an Apple logo almost. There we go. Let me just redraw B back in dotted lines. Fantastic. Okay. So that's going to be what's in our brackets. And then we're saying take all of A, right? Take this huge circle A and take away from it this Apple piece of A. So we're saying A minus like this part of A, right? That's what you're saying, which obviously is going to lead to just this middle chunk left. Since when you overlap these, you're going to find that that's the piece we're keeping. We're taking away this shaded in area. The only thing left is going to be this middle piece. And what is this middle piece? Well, this middle piece was originally the intersection between A and B. So that appears to be true for this case. So what if A and B don't have any intersection at all? Well, what does it mean to take A minus B? Well, it still means that you're going to take all of B, and what you're going to want to do is get rid of it all. You're going to want to basically erase all of B. And then you're going to be left with basically saying, well, this is what you're left in the brackets. So you're just saying A minus A. That's what you're left with, right? Because you're only left with A. And what do we know? A minus A is just going to be the empty set. Fantastic. Okay, so we should get the empty set on the right-hand side. Well, if we have A and B share nothing, then the intersection is obviously going to also be nothing, which is also going to be the empty set. So it's also going to be true for when A and B don't share anything at all. What about if one of them is completely a subset of the other, like these cases, right? Let's take the case where A is going to be a subset of B. Well, A minus B is going to be A and taking all of B away from it, which is just going to be all of this, right? You're taking all of B away, so you're going to be left with literally nothing. So you're saying A, if this is leaving nothing, then you're saying A minus nothing. Well, that's just going to leave you with A at the end of the day, right? You're going to be left with A. Okay, so since we're going to be left with just the set A after we subtract nothing from it, what about the right-hand side? Well, what does A and B share in common? What part of this diagram has both A and B? Well, it's going to be just all of A. So in this case, yes, it's going to be true that the left-hand side, you're going to be finding that A minus B is going to leave you with nothing, and then A minus nothing is still going to give you A. The right-hand side, A intersect with B is just going to give you A, so A and A, you're getting A on both sides. Okay, so that's true for this case. What about this last case here? Okay, well, A minus B is going to be taking away all of B, so you're going to be left with this hole here. Okay, and then you're saying since A minus B is going to be A with this hole, you're basically going to then say A minus this hole. So you're saying A, which is going to be this whole piece, minus another A that's just going to be A with a hole in it. So what happens if you take an object and you take another object and there's a hole in it? Well, you're just going to be left with the small hole, right? That's all you're going to be left with, which is going to be B. So the left-hand side is going to let us equal B. What about the right-hand side? Well, what do A and B share in common? Well, it's going to be all of B. So it looks like you're going to get B on both sides. So it does look like this statement is going to be true for all the examples I can think of. So let's go ahead and actually prove this. So to start this proof, we know it's an equivalence, which means that you have to prove the left side has everything on the right-hand side, and the right-hand side has everything on the left-hand side. Or, mathematically, you have to show the left-hand side is going to be a subset of the right-hand side, and vice versa. You have to show the right-hand side, A intersect with B, is going to be a subset of A minus, open bracket, A minus B. So both of these must be true, so that's what we're going to be proving to show that the statement is going to be true. Notice that this is a for all proof because we're looking at any set A and B, so we're going to start with a let. Let A and B be sets. Fantastic. Now we can get into our first case, which will be showing the left-hand side as a subset of the right-hand side. Okay, so how are we going to show this? Well, let's write out our sketch of our proof. We need to show that everything in this set is going to be in the set A intersect B, which means that we can create an element X that's going to represent every element in this set. And if we can show that X can also be here, then since X represents every element in this set, then we've shown that every element in this set is going to be in this set, which makes this set a subset of that set. So this is our start, and this is the goal we want to get to. Fantastic. Okay, so how do we do this? Let's begin by first breaking apart our start. What does it mean for an element to be a member of this set? Well, it means that X is an element of A, and X is not an element of B, which is what the brackets mean. And then we want to say that in those brackets, X is an element of A, and X is, I need to make more space actually, X is an element of A, and X is not going to be an element of whatever is in this bracket, right? X is not going to be in here, it's going to be in here. Fantastic. So we've shown that X is going to be an A, and X is not going to be an A and not going to be... Oh, actually, okay. What I'm wondering is because there's a not here, X is not in here, whether that flips these, it reverses these. It means that X is in A and X is not in A, but X is not in B, which means X is in B. Is that how that works, I'm wondering? Can you just like transfer that like negatives, like two negatives make a positive, a negative and a positive give you a negative? Need to think about that. Because what we're trying to show is that this clearly means we need to show X is in A and it's in B. Well, we have the A part. We just need to get the part where X definitely has to be in B. So I think maybe my argument works here that if X is in A, for X to not be in X to be in A, it means that X is not in A. And for X to not be in B, but then for X to not be in B means X is in B. Right? Let me verify that. So after some more thought, I think this makes sense. We're basically saying X, oh wow, that's a much brighter marker. Let me actually rewrite this so it's a lot clearer to see. Where's my eraser? Okay, so when we're saying X has to be an element of this set, we're saying X is in A and X is not going to be in A minus B. Now, for X to not be in A minus B, it must be that X is in A X is not in A or X is going to be in B. So just one of these has to be true for this to be true. Now we know X cannot not be in A because we've already confirmed X is in A. So the only way for X to not be in this set is for X to actually be in B. So this means that when we say this, X is in B and X is in A, so we get to our goal. So let's put that into actual words. First, we'll start by supposing our representative element X. We'll say, suppose X is an element of A minus B. Fantastic. Then we can now break down what that means for X to be in this set. We say then X is an element of A and X is not an element of A minus B. Fantastic. Now we can say for X to not be an element of A minus B, it must be X is not an element of A or X is an element of B. Fantastic. Since we already know X is an element of A, right? We know that from the other half of that set. Then it must be that X is an element of B for X to not be an element of A minus B. So then X is an element of A and X is an element of B, making X an element of A intersect with B. Thus, now we can conclude what we wanted to show. A minus B is a subset of, not equal to, I keep writing that down, it must be a subset. Fantastic. Of A intersect with B. Okay, we've shown the first half of our proof. Now let's do the other half. Okay, so in order to show that the right-hand side is a subset of the left-hand side, we have to show that any element, for example, y on the right-hand side, is also going to be on the left-hand side, similar to how we did the first case. So let's break this down. What does it mean for y to be an element of A intersect B? Well, it must mean that y is in A and y is in B. Fantastic. So great. And now we can say, well then, this must be true, that obviously that y meets that it has to be an A, and y cannot be an A minus B because y is in B, right? So we can then say y cannot be an element of A minus B since it's already in B, which then means that's true, and y is already in A, so there we go. I think we've gotten from our start to our goal, and let's put that into words. So we'll start by supposing our representative element. We'll say suppose y is an element of A intersect B. Then let's break down what that means. We say y is an element of A and y is an element of B. We can then say since y is an element of B, then y cannot be an element of A minus B. Fantastic. So, and given y is an element of A and y is not an element of A minus B, y would be an element of A minus B. Fantastic. This means A intercept with B is a subset of A minus B. Fantastic. Okay, we've proven both the first case and the second case are true, which means that our equivalence statement is true, which means our statement is true. So let's quickly write our conclusion. Our conclusion is going to be that in conclusion, since A minus B is a subset of A intercept with B, and what we've just proven here, A intersection B is a subset of A minus, I don't know if the camera's picking this up, A minus B, then you can write down A is equal to, open bracket, A minus B, close bracket, is equal to A intersection B. Fantastic. So we've shown here that this statement is in fact going to be true.